Last video we took a look at the law of specular reflection and discussed how to locate images for a flat mirror. Now I'd like to turn my attention to spherical mirrors. These are curved mirrors, and it turns out the actual shape that you almost always want is either a parabola or a hyperbola. But I'll talk about that in just a second here. So let's say you've got a curved mirror. If you've got light coming in from some distant source, you'll have a whole bunch of rays coming in parallel. And what you would like them to do is bounce off the mirror so that all converges to a single point. Remember, we can treat these as rays coming in parallel because if we're far enough away, like say the sun or something like that, it's a plane wave. So anywhere on the plane you can erect a ray and they'll all be parallel. So anyway, this point here where all the rays come to a focus gets called the focal point. And this distance here from the focal point to the mirror is called the focal length. Now this particular shape of mirror is a concave mirror. It pooches in like a cave is how I remember that. Now, the whole point is that every single one of these rays is going to obey the law of reflection at this exact point. So as we go along curving, the normal curves with it. This changes the angle we're reflecting through. Now, in order to get everything to go to a point, the usual shape that you're going to end up needing for this is a parabolic shape. However, parabolic mirrors are expensive to grind, and so, but it's very, very inexpensive to grind spherical mirrors. And if you keep the section of mirror small compared to the radius of curvature, then it turns out that the spherical shape here isn't too different from a parabolic shape. So so we'll also go ahead and just while we're at it, dimension in. This is our radius of curvature here. And this focal length we will see later is equal to 1/2 the radius of curvature. So this point out here would be our center of curvature. Whoops. So this point over here would be our center of curvature. So the way I drew this is probably curved in a little too tight. It should already be looking a lot flatter. All right, so let's go and take a look at how to draw ray diagrams, which will allow us to graphically locate images. And in fact, if you carefully draw a ray diagram to scale, you can just plain get the answer that way without having to do any math at all. Now, when we draw ray diagrams, I like to take a look at 4 cases. So the first case I want to take a look at is where the object distance is greater than 2 focal lengths and the focal length is positive. When we discuss the left light convention, what that means is that that will be a converging mirror. So let me go ahead here and start by drawing in my optical axis like so. Let me go ahead and draw in a mirror. Yeah, something like that. we'll say the center of curvature is here, which should put our focal point halfway in between. All right, so it turns out that when we did for the plane mirror, we used 2 special rays. It turns out that in these more general curved mirror cases, we'll actually want to use 3. So here, where the object is located at more than 2 focal lengths away, that means it's outside the center of curvature of the mirror, like so. So our 3 special rays are the Peraxial Ray, which we saw before. This is the ray that is parallel to the optical axis. So the Peraxial Ray, because this is a ray that came in parallel by the construction of a mirror, will bounce out through the focal point. Like so. Now, we've already encountered the central ray, but well, actually, we'll hold on the central ray for just a second. Let's introduce a new one. This one is the focal ray. Oops. Come on. There we go. So the focal ray will go in through the focal point, which means it comes out parallel when it reflects. And why is that? Well, it's because if we imagine reversing the process, if this ray came in parallel, it'll go through the focal point and just happen to graze our point of interest. So reversing it back around, a ray that goes through the focal point has to bounce out parallel. And then finally, your truest, bestest friend will be the central ray. So again, that is the ray that is directed from the focal point. Come on. It's directed from the focal point. And there we go. No idea why it didn't want to give me a straight line before. Let's try it one more time there. There we go. Directed in from the focal point and back out. And this one's easy to locate because you go as far below as you do above, and it goes right through that point. And you can see that all 3 rays will converge at this point right here. This means that if you were to put a screen right here, like say you're in a movie theater or something like that, if you were to put a screen right here, you would actually form an image. So we can go ahead and locate our image here. There we go. There's our image. And this image is real because it can be formed on a screen. It is inverted. We can see it's upside down. And if we look, we see this is shorter than this one. So we say it is minified. And this is worth committing to memory. If you have a case 1 situation, it will always be the case that your image is real, inverted, and minified. So if you don't get that when you draw a diagram, or if you solve a problem numerically, which we'll get into in the next video, then that means that you made a mistake and you need to go back. So these prototype cases are really useful sanity checks. Sorry about that. All right, so let's go ahead and take a look at our second case. This is where we are between the center of curvature and the focal point, and it's still a converging mirror. So let's go ahead, draw in our optical axis. I'll try to do a better job of drawing a mirror this time. Yeah, maybe something like that. So again, we'll mark out a focal point, and the center of curvature would be that far again over here. So now I'm going to make my object kind of small just so the diagram doesn't go nuts. I'll put it right here. So our object is located between the center of curvature and the focal point. And again, we can, in case 1 and case 2, we can use the exact same 3 special rays the exact same way. For the other cases, we'll have to modify some of these things a bit. But the Peraxial Ray will still reflect out through the focal point. The focal ray will still reflect back, parallel. There we go. And then the central ray, again, you can locate the point it's going to want to go through by saying as above, so below. Now, in principle, you only need 2 of these rays to locate it. We're only ever using the third one as a check. So it comes in, so the angle in has to match the angle out. There we go. So, all right, when we form our image, we see again, it can be formed on a screen because the rays are parallel. Or, sorry, the rays all converge to a point. So the image is real. It is inverted. And it is magnified. Alrighty. So now let's go take a look at case 3. In a case 3 situation, again, we have a converging lens, so that will mean its focal length is greater than 0 once we get to assigning, how to assign numbers. And the object distance, the object is located inside the focal point. So this would correspond to, say, a situation like using a contact lens mirror or something like that. Or when you're trying to put your contact lenses in and you're looking in that kind of a curved mirror, your eye is usually parked well inside the focal point. So I'm going to go ahead and I need a little bit of room here. There we go. Oops. Yeah. One more time. There we go. So here's our focal point. We'll go ahead and map out our center of curvature twice as far away, although it's not really needed here. And we'll locate our object somewhere inside our focal point. Oops. There we go. So again, the same three rays apply. So the Peraxial Ray will still come in parallel. And it'll still reflect back out. Oops. Through the focal point. But now the focal ray is going to be a little trickier. Remember, the idea of how we got the focal ray was we said, oh, we're just reversing it, and we're basically identifying that if we had this ray coming in parallel, here it would bounce out through the focal point and just happen to graze the point I need, and then we reverse the process. So in this case here, the focal ray is going to have to be aimed away from the focal point towards the mirror. So I usually like to draw, I'll use dashes for something else, but I like to draw dots here just to help me align that a bit. There we go. So it comes in from the focal point and it's going to go out parallel. There we go. And then finally, the central ray is still our truest, bestest friend. It will come in at the intersection of the mirror and the optical axis and bounce out at matching angles. So we can locate that by going as far below as we do above. There we go, just putting in a little dot there. And then angle in equals angle out. Now what we get here is we can see clearly these rays are never going to converge to form an image on a screen. So in order for us to see the image, we're going to have to look through the optical device. So this is like when you're looking at that contact lens mirror, you see your enormous eyeball behind the mirror. That's where the image is going to be located. So let's go ahead and, just like when we did with the flat mirror, what we're going to have to do is see where are these rays coming from. So what you do is you backtrack, and I like using long dashed lines for this. You backtrack the reflected rays to see where they're coming from. So this one is originating from some point somewhere on here. We don't quite know where yet. And we'll just go ahead and backtrack the others. Again, following along there. There we go. So we can see that all these rays do originate at a point. So that means if you look through the mirror, you will see an image located behind the mirror. Come on, draw in a straight line. There we go. So this is a virtual image. It is upright. And it is minified. Alrighty. And so then finally, case 4 is any mirror that is a diverging mirror. So these are like, if you say are in a parking structure and they've got those mirrors that they place strategically to help you see around a corner. This would be one of those. When we get to how to assign plus and minus signs to distances, that will correspond to a negative focal length. So here, let me go ahead and draw in our optical axis. There we go. I'm going to note my center of curvature and my focal point. The focal point is still halfway between the mirror and the optical axis like so. And the object is just literally anywhere in front of the mirror. There we go. So again, we'll be doing this the same way, but now keep in mind the idea here for locating the focal point is when parallel rays of light come in, they're going to bounce away from the focal point. That's what we mean by a negative focal point here. So for instance, if we follow the Peraxial Ray in, there we go. It is going to bounce off the mirror lined up with the focal point. And I'm drawing a dashed line here because I'm already backtracking this ray because I know what's going to happen. So the focal ray is going to be the same kind of idea. So using the same sort of logic we had before, a ray aimed towards the focal point will bounce out parallel. So that would be like that, but then we'll back it up to there. If you want, you can draw dots, but don't draw dashes or else you'll get yourself confused. So the focal ray bounces in, is aimed toward the focal point, and it will bounce out parallel. And then finally, the central ray is still your truest, bestest friend. It still works exactly the same way. It will bounce out as far below as it does above. Oops. There we go. As far below as above. There, something like that. So again, same deal. The rays are never going to come to a focus. So we definitely don't have a real image because we'll never form them on a screen. But we can look back. If we look through the mirror, we will be able to locate an image behind the mirror. So again, same deal. We backtrack the reflected rays to see where they're coming from. There we go. And then we locate our image right here. And so we see that the image is virtual. It is upright. And it is minified. So this leads to a bit of a question. Whenever you, in cars that are made for use in North America, the passenger side, the passenger side mirror is required to be one of these convex mirrors. This is because it allows you to have a little bigger angle, a little bigger field of view, so that you have a better chance of seeing any cars merging in from the side. Interestingly, mostly because of higher speed limits, European cars are required to have a flat mirror on the passenger side. But cars for sale in North America are required to have a convex mirror like this. And remember, concave goes in like a cave. Convex is there to vex you because it goes the other way. So in any car that's meant for sale in North America, the regulators in both the U.S. and Canada require the warning that says objects in mirror are closer than they appear. Well, if we look at this, that doesn't make a whole lot of sense, right? We can already see from the ray diagram here that the image distance is definitely closer to the mirror than the object distance. So why would the regulator say it's closer than it appears when it's already closer than it actually is? Pause the video and get back with me. All right, so what's at issue here is how your brain actually calculates distances of things. It turns out that using focal information from the eye and using triangulation from the two eyes in the stereo depth perception actually only lets you be able to locate things using those physical techniques out to maybe a meter or two. You get much past that, your brain switches to a different strategy where it compares the apparent size of the thing, how big or small of an angle it takes up in your field of view, up against just a wealth of experience of how big those objects typically are. In other words, because the image is small, your brain doesn't perceive it as like a tiny little matchbox car a few centimeters behind the mirror. Instead, it says, oh, this is a regular car, but because it's so tiny, it must be really far away. And so thus you run the risk of incorrectly estimating how much distance you have to get over and merge back into the right lane. And so you run the risk of cutting somebody off and making them very upset with you. So remember, always head check before you change lanes. All right, so in the next video, we will go ahead and do this numerically. Catch you over there.